going to talk about friction so that we can do some things with friction. And we could talk about Coulomb's experiments. So, I mean, there's different models of friction. In fact, people study friction in a big way. I think it's called tribology. And it's all about friction. So this is in Greenwood. He's got a little bit of stuff about friction, which is helpful. I guess we could say a little bit about Coulomb's experiments. So what did Coulomb do for his experiments? He was pulling on masses. So here's this mass on a flat surface, but we'll put, right, the mechanism of friction has to do with that interaction with the surface. So he was pulling on one side with an active force. So let's call that FA. This thing is being pushed down with mg, and then it also has a normal force pushing up on it. I think that's exactly balancing. And what he noticed is that he could pull with some force FA, and this seemed to be exactly balanced by a force of friction up to a point. So if we were to just sketch what he saw in terms of magnitudes, so here's force of friction and the applied force. What he saw is that this was a straight, slope 1 curve up to a point. And what was that point? So here n is, the magnitude of n is mg. So what he found was that this was, let's call this mu s times n. So that's the static friction. Up to that point, it fell down to what we call mu d, the dynamic friction, and then it just sort of stayed that way. And in our modeling, we just sort of combine these into one thing called mu and forget about the static versus dynamic. But it is important. They're usually slightly different. So we'll just assume that mu s equals mu d. The static and dynamic friction are the same thing, and it's just mu. What Coulomb observed, we could just try to summarize that. He tried different things. I've got some things here maybe we'll look at. Like I have an eraser, and then I have a block of wood, and I guess my iPod case, earpod case. What he found is that, and he conducted hundreds of experiments, that the frictional force was approximately independent of the contact area. And that's significant. That's a big simplification. He also found that the frictional force was approximately independent of the velocity magnitude. So as this block, I've got another piece of wood here, as this block were to like move across this piece of wood, he found that the force of friction was approximately independent of that velocity. So here's like two major ones. So it's approximately independent of velocity magnitude. The direction matters because this resists velocity. And And he found that the coefficient of friction depends on the pair of materials. And that's what this thing mu is. This is the coefficient of friction. So you can experimentally determine this. The pair of the interacting materials, you know, the materials in contact. So if it's wood on wood, or plastic on wood, or rubber on wood, right, you'll get something different. Or if you have metal on metal. So, I mean, here's some just approximate things. Here's materials, and then mu. Just make a little table. And these are just ranges. You could look it up for specific things. So metal on metal, it's been found it's about 0.15 to 0.6. If you think of tires on the road, so rubber on concrete, it's about 0.6 to 0.9. And then there's others. We could fill that out later. In fact, we'll do an experiment later. Let me show you something else about kind of what's going on. If we have the material, here's the thing that's being dragged across the other material. If you were to look at this part that I'm just putting X's right here, but if you were to zoom in on that, say like, what's going on there? And this is a crude understanding, but often that's all I have. Is there's like nooks and crannies, there's bumpiness, and these things sort of run into each other. And so you have, it's actual physical contact between these things. So as you're dragging one material across the other, because this bumpiness of surfaces tends to be roughly statistically the same, that's why you get this independent of contact area situation. So these things kind of, it gets stuck, but gets stuck at kind of a constant rate. And those who study this in detail, the tribologists, would know more about that. Because I think there are situations where you do have to consider the contact area. If this is your area of expertise, then you know more than me. But friction it's a good thing. Without it, we'd be slipping and sliding all over the place. It'd be hard to get anything done. I've done some work on human biomechanics, and I know that there's, like, if a floor is slippery, you fall, right? There's a list, if I can find it. Yes. Where is it? Yeah, this is I think this actually comes from an advertisement for people who will do treatment of your floor at your workspace so that people don't slip. That's why it says up here, if you can read it, after our treatment. So this is showing the coefficient of friction going from low down here to high. And so they have this kind of color coded, like, oh, this is dangerous. You don't want to be here. It's bad. And they say this is ice, somewhere near the bottom. Typical tile floors, this is why you tend to slip on tile floors, are in this range, 0.25 to 0.5. The ADA guidelines say that you need to be at 0.6. But I think OSHA only demands, that's the Occupational Safety Health Administration, I think it recommends 0.5 or somewhere near 0.5 for safety. So that's the recommendation for workplace floors. between your shoe and the tile. So yeah, when it says typical tiles, it's like, well, that also depends on the type of shoes you're wearing. If you're wearing bowling shoes, it's going to be really low. If you're wearing certain good work boots, then it'll be fine. And so companies will say, you know, after our treatment, I don't know what it is. Maybe they're spraying the floor with something very sticky, rubbery. Then you'll be up here in the safe range and no one will sue you. This is, I think, a lawyer slipping, dropping his briefcase. All right. And we can write Coulomb's law. Let's write it. Let's write Coulomb's law. This is a very simplified form, and it's the form that you have been using. And we'll just do it this way. Here's surface 1 and surface 2. We've got the force of friction, and I'll just write the magnitude basically. And then suppose you're tracking where this thing is with respect to some other location. So we'll describe how this is moving in terms of x, and then we have a normal force. Okay, so we'll write this in terms of x dot. What is x double dot, and then the force, and then some description. So if x dot is less than 0, it means we're moving to the left. Doesn't matter what x double dot is. The force friction is equal to mu f, mu n, sorry, mu n. And this is left sliding. So we're just writing magnitudes. The direction for this would be, it's positive, right? If x dot is greater than 0, so that means we're sliding to the right, then it doesn't matter what x double dot is, this will change signs and we'll have negative mu n. That means it's resisting the right sliding by being the other way. What if x double dot equals 0? If x dot equals 0, so if you're at rest, but there's acceleration to the left, then we've got left sliding again. And F, force of friction, is mu n. Again, if x double dot is, if x dot is 0, so velocity is 0 and acceleration is to the right, then we have right sliding. And if both of these are just equal to 0, then the magnitude of the force of friction is just going to be less than the magnitude of mu times n. So when we're in motion, we're on this thing called the cone of friction. When there's no motion, we're inside the cone of friction. So think of up here, we've got the normal force. Here's our surface. There are these two edges, and this is mu n, this is negative mu n, and the force of friction will be a sideways component, but that the total resultant force is going to be somewhere inside this. So if we're inside, this is inside cone of friction, no motion. If you're on the cone of friction, then there is motion. And we'll hopefully make this more clear with some experiments, and this doesn't look like a cone. We're doing a 2D cutaway of a cone. Let me give some other pictures that maybe help out here. Yep. This is, I've used different notation from this. So this is, I would call this F, and this is the normal. So this is the opening angle, this angle, theta. The opening angle of the cone of friction is theta equals 2 inverse tangent or arctangent of mu. So this is just a 2D view, cutaway of the cone. I've also got an image of the cone. So this is showing a block. Oops. There we go. It's showing a block and then this cone of friction. So this is a 3D view. Ooh, I'm going to draw red. 3D view. Cone. And I think a good way to kind of see this cone is you can do an experiment. And you can do this at home. I've got this wooden block, wooden plank, and I could put different things on it. So that's what I'll do. Different things on this wooden block, like another piece of wood. So this is just a wooden block. And depending on how I tilt this, it'll be different angles. And there'll be some angle at which this will slide. Oh, there we go, it slid. So what's actually going on here? Let me draw the setup. So we can, I don't want red necessarily. This is my plank, and I have a plank of wood, but it have an opening angle of, or the angle for the plank with respect to the horizontal is phi. So I've got for my object here, whatever it is, I've got gravity that's only pointing down, but the force of friction only depends on the normal force. So the normal force here is going to be a component of gravity. And we can find out at what angle this starts sliding. That's the inverse tangent of mu. So you can determine mu experimentally. Here, I just have wood as one of my surfaces. So all I'm going to be computing is the Coulomb friction, the coefficient of friction of wood with something. And sliding initiates when phi equals inverse tangent of mu. So it's the half opening angle of the cone of friction. So everything inside of that, I have where's my vector? Here's a vector. So if I've got my block And this is the normal force. The normal force will be decreasing in magnitude as I go to higher and higher angles. Right, because gravity is downward, but we're only looking at the normal part. So it's bigger, and then it's smaller. And at some point, we start sliding. So for this thing, this is wood on wood, and I get it sliding. I don't know what that angle is. Like 20 to 30 degrees or so. So wood on wood. I'm going to do another kind of table like we did above. Got angle and then mu. It's something like 20 to 30 degrees that it starts sliding. So that leads to a mu of like 0.3, I don't know, to 0.6. What about rubber on wood? Let's try that. I've got a rubber eraser, just a pink eraser. Put it on here, right? It's independent of the contact area and orientation. So I'm starting it at 0, go up, up, up. Wow, it's holding on pretty tightly. Okay, it's starting to slide. You can't even see it really. It's starting to slide. There it is. So it started to slide like at 45 or 50 degrees. So what was that? Rubber on wood. So that would definitely meet the OSHA requirements. You've got rubber soles on wood planks. What do they call that? Wood flooring. So it's about 45 degrees. And right, what's the inverse tangent of 45 degrees? It's 1. So it's pretty good. For fun, let's try. If you have an ear pod thing, they're very plastic. Not super awesome. Okay, so here we go. Putting it on here. And what's that, about 20? Okay. Definitely the least friction. So I don't know, that's plastic on wood. What do we want to say, 15 degrees? And I don't know, it's something small. Something small. And maybe you're wondering, like, what's this crazy set of formulas up here for writing Coulomb's law? Can't you just make it easy? I'm not using that when we do stuff for homework. Yeah, that's okay. You can summarize, for most intents and purposes, Coulomb's law. This tricky stuff about initiating motion, you know, people fuss about it. Usually what we're talking about is motion has already been initiated, so what is the effect of friction? But here's how you would summarize Coulomb's law. You'd say the force of friction, and it's always tangential to the surface, is going to be negative mu normal force sine of x dot. So if we're, whoops, doesn't matter what angle this is at, we're talking about, here's x, here is our object, and what is the force, what is the direction of this force of friction? Well, first of all, it's tangent to the surface, and it's going to resist motion. There's a normal force, and you know, sine of x dot, hopefully this is obvious, it's 1 if x dot is positive. It's -1 x dot is less than 0, so negative, and it's 0, x dot is 0. Another way to put this, you know, for phase portrait plotters, because I think MATLAB understands, there's some command called sign. I don't know if it's SGN or SIGN. But sine of x dot can be written as typically x dot over magnitude of x dot. This is, of course, undefined at 0, but leave that aside. Okay. When you do the experiments carefully, let me plot this, because this is just an approximation. If you do the experiments carefully, so we've got x dot, and then here is the force of friction. What you would see, or at least what we've written up here, what have we written here? We've written here that we've got mu n for negative x dot, and then negative mu n for positive x dot. And if you want, we put a little circle here because nothing is defined at 0. Experimentally, what you'll see is that there's sort of like, there's this bump, it goes down, there's a bump, and then it actually increases. So that's my artist rendering of an experimental curve. So it looks different, it's more realistic, but we're not going to implement something like that. You get the basic gist when you do just this up here. Okay, it's good enough. It gives you things that are qualitative. What's happening here at these ends? At these ends, now we've got something that's becoming proportional to x dot, right? One of the main things here is that when this is flat at plus or minus mu n, it's flat. It's independent of x dot. But at some point, you get things that are proportional to x dot. I don't, maybe linearly, maybe it's something else. So that's when you go into this regime of like viscous drag. So it's kind of linear in x dot over here and linear in x dot. But just to get things qualitative, in this middle regime, it's definitely nonlinear. And a step function is nonlinear. So Coulomb friction is upsetting because it is nonlinear. But like I said, without it, there'd be lots of lawsuits, be sliding and couldn't get a grip on anything. And I want you to get a grip on things. Okay. Are there any questions about Coulomb friction? Next, I'm going to talk about how they affect phase portraits. Okay. Any tribologists in the audience? There's these ancient sea creatures called trilobites, and so I sometimes get trilobite and tribology mixed up. So when you add friction, and I'll post some material on this, when you add Coulomb friction, it does have an effect on phase portraits, and it's kind of interesting. Let me give you a spring mass system where we add friction. So we've got our spring mass system. X is the the distance from equilibrium of the spring. Which, you know, typical. Let's use Newton's second law. And this is a mass M. We've got a normal force N, which is going to be equal in magnitude to M times G, right? So gravity is here. Newton's second law would give us mass times acceleration equals the spring force and then the Coulomb friction force. So according to the compact way that we said we could write it up above, this would be mu times N, but N is just mg. And then sine of x dot. And in for this, we could put x dot divided by magnitude of x dot for most intents and purposes. And what would we find? If you were to release this spring from rest, let's just look at what would happen. So here's x as a function of time. I'll put this in blue. So let's say I pulled on this spring, release it from rest. This thing will oscillate with, it's getting lower and lower. And then at some of it, one turning point, it'll just stop. Like, what's going on? Okay, here, after reaching rest in a certain zone, it stops. Why is that? Well, this is related to that cone of friction thing. At this point, the effect of the spring isn't enough to overcome the friction force. So motion just stops. So let me put a dashed line. And I'll color this in yellow. If the thing comes to rest, so if there's a peak or a valley in terms of this thing in time, that means X has instantaneously come to rest. And if it does within that zone, then the thing stops. So there's this region of equilibria. And in fact, this is mu mg over k and negative mu mg over k. So you would get that from a cone of friction analysis. So we have this range of equilibria, which is kind of interesting. So instead of having one equilibrium point, if there was no Coulomb friction, this thing would oscillate forever with an equilibrium point at the center. Right, that's what the oscillations would look like in terms of a phase portrait. But now in this case, we don't have that. So if we were to plot x and x dot, what we'd find is there's now this range of equilibria. We'll put it as a yellow bar. And it's on the x-axis. It's all at x dot equals 0. So if we start somewhere, like here, and then follow this around, at some point it'll just sort of run into that and it'll stop. So we'll have oscillations that go for a while and then stop. So that's what the phase portrait looks like. It looks kind of like, instead of things all spiraling into a point, they spiral into a band. And these are, of course, at mu mg over k, negative mu mg over k. So instead of a single isolated equilibrium point along the x dot equals 0 line or the x-axis, we have a range, a band of equilibria. And where you end up depends on where you released. Okay. I think I have some actual figures of showing that. Oops, maybe not that one, this one. So this shows an actual phase portrait where you've got the background arrows, and it looks kind of weird, but yeah, this is an actual simulation. All right. How about other exotic situations? So here's an example. Which one's this? The whirling tube with friction. So we've seen the whirling tube problem, but I think before we didn't consider friction. If you now have the whirling tube with friction, so the phase portrait before, maybe you don't remember, phase portrait before, let me do R dot versus R. So this is with mu equal to 0. There's just one equilibrium point, and the phase portrait looks something like that. It's symmetric with respect to the R axis. It looks like that. There's just one equilibrium point. And I think there was a homework where you were asked, okay, what's the minimum point, the minimum velocity to release right at the bottom of this shaft to make sure that this thing shoots out, and it would be like right above the trajectory that hits the equilibrium point. Okay, so this is for mu equals 0. And there's an end of the tube over here. End of tube. I don't know what that is. R end. Now, when we include friction, Coulomb friction, this picture will change. And you could probably guess how it's going to change. Instead of there being one isolated equilibrium point, we're actually going to have a band where if the marble ends up in there at 0 speed, it's going to stop. Or if it starts there at 0 speed, it's not going to go anywhere. So here's our end of the tube. We have now, instead of the one point, it's kind of like around that point, we have a range of equilibria. So the phase portrait's going to look kind of weird. I'll color in orange sort of the end. So this one hits that end, and then we have something hitting the other end. And then going downward, we also have, we have orange. It's going there, it's going there. So everything inside this sort of orange lane, these are trajectories that are going to end up, we'll color them in cyan. They're going to end up at the equilibrium point, the range of equilibrium points. And then things that are outside of that will not. So they will do other things. Something like that. So this is for mu not equal to 0. What does this range correspond to? It's going to correspond to some range of points over in the tube. Where if you, like I said, if you start there at 0 speed, you'll stay there. And There are also trajectories, these blue ones shown here on the right, that'll end up at that band of equilibria. And right, the equation of, you have to be careful about this because this is a tube whirling around. So the normal force, oops, if you were to actually write this, normal force, which you could get either from Newtonian or careful analysis of Lagrange multipliers. The normal force is due to the spinning of the tube. On the bead and gravity. And right, this mu would be related to how does the interaction between the bead and the inside walls of the tube. So what you'll get for R, you'll get an equation R double dot equals some stuff, and then the Coulomb friction part would be mu n sine of R dot, where of course sine R dot, you could typically write it as just R dot over magnitude R dot, because that gives +1 or -1, whether this is positive or negative. And usually it's well behaved close to 0. Okay. So now there's a range of equilibria. That seems to be what happens when you add friction. You have, instead of one isolated point, this range, and it's kind of odd. Okay. I'm going to look at this falling rod, the falling baton. And just for fun, we'll consider the phase portrait of the falling baton. You're not asked for the phase portrait in any kind of homework, but it is interesting to consider. So here's our falling baton. And there it is in all its glory. I actually tried this experiment by having a broom fall, and it did seem to match the intuition that it does come away from, the handle came away from the wall first and then hit the ground. The whole hitting the ground part is really quick though. So what if we were to plot, right? We've chosen somehow tracking this angle theta is the best. So if we look at theta and theta dot, if I said, okay, here at the initial time, we've got this initial condition, we're releasing from rest. And this is with, we'll start out with mu equals 0. There's no friction. But we should probably draw it here. This is 90 degrees. I'll use degrees just because it's intuitive. For the calculations, you want to use radians, but 90 degrees. If we start out here, theta naught equals 5 degrees at sometime t0, then what we'd find is before we release from the wall, this thing's it's going to be moving. And then at some point we will release from the wall. And the angle at which that happens, theta s equals, it's like 48.38 degrees. And then this will keep moving, keep evolving, and it'll actually be steeper until we hit the wall. And if you want to see a movie of that, because it's so cool, here is a movie So this is showing baton releasing from the wall and then impacting the floor. So it starts at 5 degrees. I'm showing this reaction force of the wall. And then at some point, it releases from the wall and then quickly hits the ground. It all seems to happen in around 1.17 seconds. Let's try that again. Right, it releases at like, I don't know, 0.96 or something. And then just a fraction of a second later hits the ground. So that's that one trajectory, right? We call this ending point. This is T impact. Whoa. T impact. And T impact minus T0, I'm getting like 1.17 seconds. All right. This isn't quite a phase portrait. It's just showing one particular trajectory. What do the other trajectories do? Well, if we were to release, you know, let's say at theta equals 0 degrees, this will do something similar, but then it'll reach, it'll separate from the wall sooner. So there's actually this frontier of points that correspond to separating from the wall. And at that point, the model actually changes. If you think of it in terms of a vector field, the vector field changes. And then it actually becomes more steep. So there's a discontinuity. And so this would happen for other things too. And here, this discontinuity. So that's kind of our phase portrait. And we can't forget that this thing goes both ways. You could have negative theta dot, which means what? You're kind of pushing up on the broom and then it slides back down. So all these kinds of things happen. So this is model 1. So that's attached, when it's attached to the wall. And then model 2, it's released from wall. And so then there's this whole kind of series of patch points. Oops. Did it erase everything? Not everything, just some things. Release. Until it hits the floor. And then you get started thinking about, well, what would happen after it hit the floor? There'd probably be some kind of impact reaction. And what would that mean? That would mean, you know, this point up here instantly theta dot instantly goes to some kind of negative value, and something else goes on. But let's not think about that. That'll make our head hurt too much. Let's just add friction. So now, with friction, just mu not equal to 0. Then what? Well, what equilibrium point did we have here? All we had for the equilibrium point was theta equals 0 and theta dot equals 0. So now that equilibrium point is going to grow into a band. So let's do theta dot. This equilibrium point grows. This theta critical value is inverse tangent of 2 mu. You can work it out. So there's this whole band of equilibrium points that if you start somewhere above it, you just sort of hit this equilibrium point, then there'll be a special trajectory that will hit the edge of that. And then everything above that will actually come down and then kind of go up. It won't go up forever. In fact, there's still this frontier of points related to separating from the wall. It's this line of points that separates being in model 1 versus model 2, the attached to wall and then released from wall. So things would go up here and then come up here and then go steeper and hit this 90 degrees. And then there'd be some other model. And you could have other weird stuff, like goes up here, then it hits there. Right, there's things that can happen. This separating from the wall, I think I said it last time, this is where you technically jump from being 1 degree of freedom to 2 degrees of freedom, but due to other things, you could still represent this in the theta and theta dot. And this was kind of interesting. All right. Like I said, there's no one's asking you to make the face portrait, but it is instructive to see for this problem. In fact, if you remember, it's another thing I did. Remember that problem of the baton, the skate under it, and you can't move along there, and there's going to be some kind of force of constraint. That was one of the ungraded homework problems. Just, hey, can you simulate this? I just want to show you that. Here's a situation where we pushed it backwards and then we see what happens. But it's kind of useful to see what the force of constraint is. This is showing the force of constraint, the initial time this thing is being pushed backwards. And you'll see the force of constraint gets huge. That's worth seeing again. It gets really huge, and it's then it goes down to 0 as this is moving in the direction that it wants to move, and then it'll just move that way forever. All right. Now what? We can, I'm going to switch gear. I'm not going to talk about friction so much anymore. I want to talk about the spinning top. Here's a spinning top, although I can't get it spinning fast enough. Not this one, without, I think, a machine to get it going. Now this spinning, here's a smaller spinning top. I was able to get this one spinning. And first, I want us to think about the qualitative assessment of the motion. If I get this spinning, here's a top, if I get it spinning so that it's got a large angular momentum in the positive direction. So I use my right hand, curl my fingers in the direction of spin, and my thumb is pointing in the direction of the large angular momentum. That's the angular momentum. If I'm a little bit off from the vertical, then there's going to be a moment due to gravity that affects the motion. And what will that moment be? It would be the moment arm cross gravity. So it's going this way. So my moment's going that way. I have H going this way. And if you remember the qualitative analysis, it was that omega cross, I don't know why this keeps happening, but I don't want to know about it. Omega cross H is approximately equal to the moment. What does omega have to be? So omega cross H, this orange vector, to go in that direction. It turns out vertical. So omega cross h, my thumb is pointing in the direction of the moment. So if I start this out spinning, viewed from the top, this is spinning counterclockwise. A counterclockwise, seen from above, spinning top will, and then we call this the motion that it'll do, it'll precess. We'll have omega pointing vertical. So counterclockwise precession. And I have a little video that I made that'll show you that. If you have, this is it. If you have an iPhone, and maybe other phones have this, you can slow things down. It does slow-mo mode where it films at 240 frames per second. So here I got this spinning, and yeah, you can see it's precessing counterclockwise. It's doing some other motion too. It's called nutation. This isn't actually in the slow-mo part. Let me go to the slow-mo. Here's slow-mo. So you could see it is precessing counterclockwise, but also that tip, the tip is not only moving around, it's actually going up and down as well. And that up and down motion is called nutation. So for the spinning top, at least our qualitative assessment works. You should try it. And the usual way that I spin a top with my right hand is actually the opposite way. I actually spin it clockwise, which means I would get the opposite type of precession. But to simplify it, I really tried hard to spin it counterclockwise. Here we go. Let's find here's a spinning top. Look at that spinning top. Oops. Spinning top. We've got these Euler angles, the 2, 3, 2 Euler angles, or sorry, 3, 2, 3. We have a Lagrangian, which if we write kinetic minus potential, the Lagrangian is actually not a function of psi or phi. So those are actually gone. Although it is a function of their generalized velocities, their rates of change. Okay, so we have two ignorable coordinates, psi and phi, which are related to symmetries. And then we would apply the Routh procedure. And we would get beta sub phi partial L partial phi dot is I3 phi dot plus psi dot cosine theta beta psi partial L partial psi dot I1 psi dot sine squared theta plus I3 phi dot plus psi dot cosine theta sine. No, cosine theta again. But you'll notice, what is this? I3 phi dot plus psi dot cosine theta. That's the same thing as beta phi. So we can, as the Routh procedure tells us, we need to rewrite these two generalized velocities, phi dot and psi dot, in terms of these betas and the non-ignorable coordinates and velocities. To simplify it, and you don't have to use this, but it will lead to some simpler algebra if you do this problem. We'll define A as beta phi over I1, and B is beta psi over I1. And then what you would get for this rewriting is psi dot equals B minus A cosine theta sine squared theta. Phi dot equals A I1 over I3, a constant, minus B minus A cosine theta over sine squared theta. Looks like it's just psi dot times cosine theta. Okay. We could also, right, then you'd plug this in, use these to express the Routhian, and you could also think of these as reconstruction equations, because they allow you to, that's sometimes what they're called, depending on how you use them. Because you can reconstruct, it's not like important for the main dynamics, but you can reconstruct what psi as a function of time is and phi as a function of time once theta as a function of time is solved. And this is also based on initial conditions. Beta phi and beta psi depend on these initial conditions for psi dot and phi dot. So you would need to know your initial conditions as well. But once you write the Routhian, it'll just be a function of psi and psi dot. So the Routhian equation is actually going to give you just theta double dot. It could be written as theta double dot is some function of just theta, which means you can write this as the negative of an effective potential. So even though this appears as a complicated 3-degree of freedom problem, if you choose some other set of Euler angles, it might not work out this way. Remember, you were given that cautionary tale that depending on which generalized coordinates you use, you might see symmetries and you might not. It's known that these 3, 2, 3 Euler angles will show this symmetry for the top. So it looks like it's a 3-degree of freedom problem, 6-dimensional phase space. Oh, very complicated. But really, because of conservation of a couple of angular momenta, you can get something that looks like it's just effectively 1 degree of freedom, in that this angle, this deflection angle from the vertical, you know, the angle of this, there's a B3 axis coming out of the top and then the vertical. So that angle is really what it's all about. And then you'll get an effective potential, which has, it's good for you to figure out. There'll be a part due to gravity plus a part that's just due to the inertial effects of the other two angles. And let's call this equation star. Solutions of any equation that has that form, second order time derivative of a variable equals the negative potential energy, effective potential energy of that variable, will conserve an effective total energy, 1/2 theta dot squared plus the effective potential. If I were to sketch, and what are the limits of theta? Theta goes from 0 pointing up to pi with this points down, which, I mean, you can get very large angles of theta if you put your top on a little stand. You can get large angles. Let me just sketch what the effective potential will look like. Here's pi, and then here's 0. The effective potential is going to be U-shaped, so that's convenient. Its name is U, and it looks like a U. And then depending on what your initial conditions are for theta, there'll be an effective energy that is conserved, and the distance between these two curves is 1/2 theta dot squared, which means it goes to 0 at a couple of points. We'll call these points, instead of theta min and theta ma, I'll call them theta 1 and theta 2. Okay. And here's how you can interpret what's going on. Imagine a sphere, and we've got the pivot point at the middle of this sphere, and B3, the B3 axis is tracing out curves. So the spin axis of this is tracing out curves on the tip of this sphere, and it will, trace things out. I don't know what it'll do, something. And it's going to be going between these two angles. So remember, up here is, maybe it's not there, it's here. This is theta equals 0. This is theta equals pi. There'll be two bands. This is theta 1, and then some other band, theta 2. These will limit, this motion in theta is actually called nutation. And it's sort of interesting that it's nutation, or the dynamics in theta, that basically determine everything. So you can visualize the motion of the tip of this sphere moving around. And then psi dot, I guess we could, let me say what other things are. Motion in phi is called spin. Motion in psi is precession. We can get at the precession by looking at this, the reconstruction equation for precession. This is B minus A cosine theta. I'm just rewriting it from up above. So if B is greater than A, then psi dot is greater than 0 always. So you always have precession in one direction. Let's show a picture of that. Is it not here? It ought to be maybe here. So this is a picture showing that. What the tip of the spinning top does. I know I've gone over time, but this is the last one. If B is less than A, then psi dot will change sign. And the last thing is just showing that. And when it changes sign, then you get these loop-to-loops. So it's unclear to me if in my video, did I have loop-to-loops? Did I not? I don't know. But we can also, let's see. This is a Wolfram demonstration project that shows the spinning of a top. And you can even plot the path. So this is showing the blue arrow is the B3 axis, and you can see how it's moving around. If we increase this velocity, we're changing psi dot, and so you get these loop-to-loops, and you can kind of see it from different angles and so on. And you could speed it up. There we go. And this is approximately what I see with the top. All right. So I can stop there.